Hi everyone, welcome back, and we're moving on to question 18 in the 2019 B test. The question reads, this is probably a misprint. The car begins with an initial speed v0 and maintains a constant acceleration a throughout the race. Both v0 and a have independent uncertainties of 10%. Which contributes greater uncertainty to your estimate of the time for a car to complete the race? So in the question, in the answer choices, it gives us answer choices that depend on whether or not the race is short or whether or not the race is long, or if it doesn't depend on long or short races at all. So let's think about the uncertainty of what's the equation for the uncertainty of the time. So we have delta x is equal to 1/2 a t squared plus v naught t. So delta x is just the entire distance of the track of the race. So then if we move over to subtract by delta x plus v naught t minus delta x. And then if we want to solve for t, we will use the quadratic equation. So t is equal to negative b squared, so negative v naught squared plus or minus the square root of b squared. Oh wait, hold on. I don't remember a quadratic equation. There's no b here. I mean, there's no square here. It's negative b plus or minus the square root of b squared. So that's v naught squared plus or minus, no, v naught minus, minus the square root, sorry, minus 4ac. So the minus turns into a plus. So because of this minus sign, so plus 4, and then 4 times 1/2 is 2a times delta x, okay, divided by 2a, and 2 is 2a over 2 because it's 1/2. Alright, so just a. Let me write this a bit neater. Square root of v naught squared plus 2a delta x over a. So if we want to figure out the uncertainty in t, obviously the uncertainties of a and the velocity propagate throughout these calculations and give us an uncertainty for t as well. So let's think about how they propagate through. Let's do a first because a is a lot easier, and let's consider very long races and very short races, the very extreme cases where delta x is very, very large or delta x is very, very small. Okay, so let's first consider the case that delta x is very, very large. Well, delta x actually only has an effect on a, so and remember, so if we have the uncertainty of a product, so I'll say the uncertainty of this 2 delta x times a, the uncertainty of a product divided by the uncertainty, divided by the actual product, so 2 delta x a is equal to the square root of all the uncertainties. So obviously 2 delta x, since they're absolute numbers, they don't have uncertainty, so their uncertainty is 0, but a has an uncertainty, so delta a over a squared, and this is just the equation for the uncertainty of a product, right? So then this thing is just delta a over a. So if we multiply by both sides, 2 delta x times a, so the uncertainty in the 2 delta x times a is equal to 2 delta x times delta a, right? What this tells us is if delta x is extremely large, then that means this uncertainty is also extremely large because it has a direct dependence on delta x. And whatever uncertainty is here is going to propagate throughout the entire calculation. So say this uncertainty is infinity, then this uncertainty will also be infinity, and this uncertainty will also be infinity, right? So basically the acceleration here, matters a lot if delta x is large, right? You can imagine that if the A is smaller, sorry, hold on. If the uncertainty in A, so right, it's asking for the uncertainty in A and uncertain V naught, right? So if we can imagine that the uncertainty in A, this is the uncertainty in A. If the uncertainty in A is extremely large, that means that this delta x will also, if delta x is a large number, it will also propagate a lot. And the uncertainty of the entire equation will be largely based off this combination of this delta x and delta A, right? Sorry, this is actually sigma A, but anyways, what this tells us is that the uncertainty in A for sufficiently long races actually contributes to greater uncertainty to the estimate of the time it takes for the car to do the race. Let's convince ourselves of the opposite. So this seems like the right answer. Let's convince ourselves that the uncertainty V naught is the more important one for sufficiently short races. Okay. So for sufficiently short races, that delta x is very, very small, so we can approximate this to be approximately 0, right? So that means it will just be v naught squared square root, so that's just v naught plus or minus negative v naught, right? And this is this is actually not. Let's think about the uncertainties. I was thinking about the magnitudes, so I shouldn't have done that. The uncertainty in this product is going to be very close to 0, and the uncertainty in V naught is not going to be, it's going to be just the uncertainty in V naught, right? So basically, the acceleration doesn't really have an impact. The uncertainty in A is not really going to have an impact. So right here, the uncertainty A is going to have an impact, but we have to notice that since V naught is in this equation twice, right, the uncertainty in V naught is going to propagate more than the uncertainty in A. You can use the equations to convince yourself of this. But because V naught is here more, and there's more calculations based on V naught, then the uncertainty V naught is what dominates, given that this basically uncertainty is 0 since delta x is so small. So that tells us that the uncertainty V naught for sufficiently short races is what contributes to greater uncertainty for the time it takes for the car to complete the race.